Continue on our way to prepping you for fun and games activity number 1, which, as you well know, is this Friday. I forgot to mention this yesterday, but if you're keeping in touch with our Sockeye website, you know about this. Bonus Quiz 1 is posted. You may find questions on Bonus Quiz 1 which relate to Exam 1 and its content, but I know that all the questions on Bonus Quiz 1 do not do this. We've not yet considered the material in its entirety, which you need to be aware of to tackle Bonus Quiz 1 in its entirety. But I think you are capable of deciding which questions apply at this time and which questions do not apply at this time. How many of you have looked at Bonus Quiz 1? Aha. Did you notice a question which invited you to write equations for acid-base reactions? Did you? You think that might apply? Need I go further with this? All right. Back to buffer system analysis. We left you with this. A solution is prepared which contains both ammonia and ammonium ion as principal species which have a bearing on system pH. As you know, I hope, whenever you are invited to do a calculation for the problem in question, you must always have before you what? QPSI, period. Principal system inventory, quantitative. So you know what you got and how much. Without that, there's nothing you can do with this problem that will make sense. Here's the system. Do you recognize that in preparing this system, the molarity of ammonia as well as the molarity of ammonium ion will each be divided by 2? Because you're starting with an ammonium ion solution and ammonia solution. So if you need molarities, these molarities will be divided by 2 as a consequence of dilution. Given that, the principal system inventory tells us that ammonium ion and ammonia are the pH affecting or controlling species in this system. We can get at pH, or hydronium ion concentration, with either Ka ammonium ion or Kb ammonia. Both work. But if I'm interested in calculating the hydronium ion concentration, I'll take the Ka expression because that's got hydronium ion in it directly. If it asks me the question to get at hydroxide ion concentration or PHO, then I'll deal with Kb because it's got hydroxide ion in it directly. So, here's Ka ammonium ion. This, of course, is the equilibrium constant expression for the reaction of ammonium ion with water. Double arrows, hydronium ion and ammonia. And prior to treating with the 200th mole of HCl gas, here's the hydronium ion concentration and the corresponding pH. When we do this arithmetic, do I have to change these mole quantities to their concentrations? Since this expression contains concentrations? as do all equilibrium constant expressions, other than partial pressures, but there's no gases in here. Do I have to change these to concentrations to do this arithmetic? You need to allow these expressions to talk to you, so you will know what they mean. If you know what they mean, you'll know how to handle them. If I convert these values to molarities, I will do so by dividing this by the solution volume, 0.2 liters, and this by the solution volume, 0.2 liters. So I take what I have here, if I write it as moles, divided by 0.2 liters, what I have here, if I write it as moles, divide by 0.2 liters. I don't need to do this arithmetic. That's dividing top and bottom by the same value. It doesn't change anything arithmetically. So I can put those mole quantities in here straight away, if I understand what's going on here. There are cases where you won't be able to do this, but this is a case where you can do this. Here's the pH. Now let's add the HCl. We talked yesterday about the fact that if I take 200 milliliters of DI water and put in this quantity of HCl, I get an enormous change in the hydronium ion concentration and an enormous change in pH. A pH of 6 units, pH change of 6 units, pardon me. Change in the hydronium ion concentration of 1 million. If I put this quantity of HCl in 200 milliliters of DI water. Well, here's a 200 milliliter solution. I'm putting in again 0.020 moles of HCl. But this baby's a buffer. So what happens when I put in the HCl? It doesn't react with water to make hydronium ion. If it did, the pH would change significantly. And instead it reacts with ammonia, because that is recognized by us from our PSI to be the main base in the system. And the ammonia murders the HCl by this reaction. I wrote extent. We talked about this yesterday. What's the extent of this thing? How large? Hey, HCl reacts with water 100%. Is ammonia a stronger base than water? Yeah. Well, if HCl reacts with water 100%, it certainly reacts with a stronger base 100%. So there's no question that this reaction eliminates the added HCl, provided that the added HCl is not a quantity which is larger than the amount of ammonia in the system. Now keep in mind, I can go to the lab and I can make any doggone mixture I feel like making. I'm going to tell you this right now. With problems on exam number 1, I'm going to ask you to demonstrate that you understand this. I'm going to devise a problem like this, where I will add, for example, for this specific case, a quantity of HCl, which will be less than the quantity of base in the buffer. What happens if I add 0.080 moles of HCl? What's going to happen then? How will the system inventory? Because as you do chemistry on a system, you have to keep in touch with the inventory as it changes for each chemistry that occurs in the system. You always need to keep yourself aware of what the heck the system is composed of. That way you can understand the chemistry of the system. And without that, you cannot understand the chemistry of the system. What happens in this system if instead of adding 0.020 moles of HCl, I add 0.080 moles of HCl? Will I murder all the ammonia? But will I also murder all the added HCl? And all that added HCl would become what? What would it become? What would it become? Ammonium ion. So I would now have a system that would contain, if I added 0.080 moles of HCl, 0.18 moles of ammonium ion. So now I'd be analyzing the hydronium ion concentration for a solution of ammonium ion. No more, no less. And for that solution, I could write x squared over m sub I minus x. I can't write x squared over m sub I minus x for adding 0.020 moles of HCl, because in this system, when I added only 0.020 moles of HCl, these molarities are much different from each other. Now, what if I take this system and I say, I'm going to add 0.20 moles of HCl. Not 0.2, but 0.20 moles of HCl. Now, what's going to happen?
The first 0.08 will react with ammonia, and then the rest of it will react with water.
And so, I will now have a solution which in essence is what? Hydrochloric acid solution, a solution of hydronium ion as the main pH controlling species, right? In this solution, would I care about the presence of ammonium ion? Not one damn bit. So let's do that one right now. I imagine to add, instead of this quantity of HCl, 0.20 moles of HCl. Okay? I will wind up with a system which, beside ammonium ion and chloride ion, since it's ammonium chloride solution, and since I added HCl, a system which will contain how many moles of hydronium ion? How many? 0.12 moles of hydronium ion. Contained in what volume? 200 milliliters. That's 0.20 liters. Now watch out. There's some really fancy arithmetic. 0.12 moles of hydronium ion divided by 0.20 liters. What's that give me for a hydronium ion molarity? 0.60, if you please. You think I'm going to get angry if I see significant figure errors on this exam? It's going to cost you. You make mistakes, you're going to pay. Don't make mistakes. And don't ever defend yourself on the basis of, you know what I meant. What you got on the paper is what you meant. Period. So now I got a solution where the hydronium ion concentration is 0.60. In that case, the pH would have changed enormously. Because if I add a quantity of hydronium ion, which is equal to or greater than the base that's in the buffer, what do I do to the buffer? Is it still a buffer? No, which means I destroyed the buffer, didn't I? Okay? All right, on we go. For this problem, here's what we get for the hydronium ion concentration. Here's how we get to hydronium ion concentration. Because in adding the 0.020 moles of HCl, I kill 0.020 moles of this, so I wind up with 0.060 moles of this, and I make 0.020 moles of this, so I wind up with a total of 0.12 moles of ammonium ion. So I'll put those numbers in here directly. I don't need to turn them into concentrations. Why should I divide top and bottom by the same number? Not going to change anything arithmetically. So here's the hydronium ion concentration. 2 with parentheses. Do you know what this symbology means? This is in regard to significant figures, if I add a third significant figure. Because when you're going to take concentrations and turn them, hydronium ion concentrations, turn them into pHs, you want to keep 3 sig figs here, then do the pH and report the pH to 2 sig figs, which I did. Okay? 8.95. Here's what I had before I put in the HCl. pH changed by 0.2 units. Remember again what happened when I added the same amount of HCl to 200 milliliters of water? Ha ha! change the pH by 6.0 units. A million-fold change in hydronium ion concentration. Here, not much change in pH. All right, let's play this game again. Because I think for you to get familiar with this stuff. Because I repeat, the reason why I can do these things with ease is I've been doing them for 50 years. I don't want you to take 50 years to get good at this. I don't even want you to take 50 days. I'm greedy. I want you to be good at this right away. So I'll do everything I can to help you be good at this right away. And I think the best way to get at this right away ability is with some good practice. So we're giving you practice. Now I'm going to start with an acetic acid solution. 100 milliliters, 0.10 molar. I'm going to add hydroxide ion. You remember doing an investigation like this in laboratory? Do you remember doing an investigation like this in laboratory? Nobody remembers? Do we have to go back to lab and repeat assignment number 1? In assignment number 1 for 46 laboratory, after you got handles on pHs and hydronium ion concentrations for 1 molar, 10th molar, and 100th molar acetic acid solution respectively, we had you look at these solutions with a pH meter. Then we did this. Remember that? The idea was to prepare a buffer solution and see how it worked. See, I want laboratory and lecture to be integrated as much as possible, because laboratory is where chemistry is actually done. This isn't chemistry. This is a bunch of chalk smears on a board. Chemistry is what goes on in beakers and test tubes when you prepare mixtures in which reactions occur. That's chemistry. What we do here is to try to give you the ability to understand these reactions. What's in the lab, where you really run the reactions, where you really do the chemistry. All right? So when I do this, I'm going to convert acetic acid to acetate ion by the reaction I wrote up here. So if I kill some but not all of the acetic acid, I will wind up with a solution that's got both acetic acid and acetate ion as principal species. Do I have an acid and its conjugate base now present in appreciable molarity? Yes. Do I have a buffer then? Yes. That's what you got to do first. You got to understand the chemistry that is occurring in the system of question. That's where it's at. That's what it's all about. Chemistry. I'm very sorry to say that not much of that went on in 2045. But that's all that goes on here. This is chemistry. Now then, we are in fact told to add the hydroxide ion to the acetic acid until I get this pH, which means I get a hydronium ion concentration of how much? This kind of stuff, you got to snap this off. You can't be fooling around with pH and what's the hydronium ion concentration stuff. This is arithmetic. There's the pH. What's the hydronium ion concentration? 1.0 times 10 to the minus 5. Bingo. Okay. So, the question ultimately is, how much hydroxide ion do I need to add to achieve this buffer preparation? To make this acetic acid acetate ion buffer, which got pH 5.00. Well, we recognize this is the chemistry. Here's Ka for acetic acid. Again, I'm going to use this rather than Kb for acetate ion. I'm talking about pH and hydronium ion concentration. So I'm going to take what I wrote here and rearrange it. This, of course, is Ka. Until I get this. Here's the hydronium ion concentration at 1.0 times 10 to minus 5 molar. That's what I'm trying to prepare, right? Well, here's Ka. Which means if I make an acetic acid acetate ion solution in which the mole ratio or molar concentration ratio, same thing, of acetate ion to acetic acid is 1.8 to 1, I got it. We've now paid attention to, and I hope understood, the chemistry that is occurring in this system as we treat it with the hydroxide ion and convert it to a buffer. Okay? So now let's get at the how much part. How much hydroxide ion do I have to add? Well, how much acetic acid did we have for starters? How much acetic acid we starting with? I don't want concentrations, because this baby, which is what happens when I treat with hydroxide ion, is a mole ratio. It's not a molar concentration ratio, right? So, I'm going to rewrite this because I want to make some notation underneath the formulas in this reaction equation. How many moles of this we start with? 0.010. What's the extent of this reaction? Would you say, practically speaking, 100%? Because hydroxide ion reacts with acetic acid, very large extent. Okay? Now then, how would you like to represent the quantity of hydroxide ion added? X. Why not Y? Why not Z? Z not Y. A squared times Q cubed divided by pi factorial less I, the square root of minus 1. I can do all these things. But then I'm bordering on mania. I'm not going to do that. So I'll stick with X. Okay? So if I add X of this, and I recognize that X is a quantity that's smaller than this, otherwise I'm not going to make the buffer, I'll kill it. Okay? How much of this will be remaining after I add X moles of this? And how much of this will I make? Wonderful. Wasn't hard, was it? All we did was write this equation and let it talk to us as a stoichiometric ratio. Now then, what did this analysis show us? That the mole ratio or molar concentration ratio for the buffer we're trying to prepare is in favor of acetate ion by a factor of 1.8, right? That's all I'm going to write. This, and then, what do I write here? Does this do it? Because that ratio tells me that 1.8 times the acetic acid molarity, if I cross multiply here, will, for this buffer, equal the acetate ion molarity, or moles. This is not but simple high school freshman algebra. Okay? There it is. Now watch out, this is really a tough relationship. Solve it. X equals, I got it here someplace, 0.0064 moles hydroxide ion. Now keep in mind, but you can see at a glance if you look at question 1840 as it is stated in the notes. We're not adding sodium hydroxide reagent. What are we adding to give us the hydroxide ion? What is it? All right, source of HO minus 0.10 molar sodium hydroxide solution. Okay? Remember, when you see this label here, you're talking about a solution. And this label in its entirety tells you what? Tells you what the stock folks did to make the solution. Or what you did if you made the solution. Or what I did if I made the solution. All right? So if this is where I'm getting my hydroxide ion, and I need to get 0.0064 moles of hydroxide ion, what arithmetic do I now need to do to figure out the volume of sodium hydroxide solution at this concentration that I have to add to give me that many moles of hydroxide ion?
It tells you. Divide the moles.
What arithmetic should I do? I want a setup. And to write this setup, what technique do I apply? What's it called? What's it called? You did this in 45. Unit or dimensional analysis. You let the units talk to you. The units will tell you how to write the setup. Not numbers. Numbers tell you nothing by themselves. I told you this before. If I ask you how tall you are and you report 28, I don't know what the hell that means. Golfer, playing golf. How long is this hole? 4,007. What? $4,007 leagues? Whoa! That's one hell of a long hole. Now then, I want moles, right? I don't want moles. What am I talking about? What do I want? I want volume, right? I want to know what volume of this solution contains that many moles. So I write 1.0 liters, or if you prefer, 1,000 mLs, okay, per 0.10 moles of OH minus. That's the first factor I write down, because this is the factor that contains volume of the sodium hydroxide solution. And the volume is in the numerator. What do I do now? If nothing else, you see by this multiplication, the only remaining unit is volume. That's what I want. And the setup which I created is on the basis of this is how many moles of hydroxide ion I got to get. So now I do the arithmetic. Oh, that arithmetic looks really hard. Damn it, the battery went out. My calculator shut down. This one did. I don't care, I don't want it. What's the answer? Done. All right. Question 41. Well, 1841, since we're in chapter 18. For this, I'm going to provide you with a reminder. Recall question 1822. Take a look if you don't remember it. Question 1822 asked you about combining sodium sulfide solution with hydrochloric acid solution. Your sodium sulfide solution, PSI, besides sodium ion and water, showed you that it contains hydroxide ion and hydrogen sulfide ion. S2 minus AQ is impossible, because S2 minus is a base stronger than hydroxide ion. And so is a base which will react with water 100% extent, practically speaking, and convert to its conjugate acid, which is HS minus, while producing hydroxide ion by abstraction of H plus from water. Okay? That was question 1822. Now, we're going back to 1822. And recognizing that the difference between question 1841, this one, and question 1822 is what? What's the difference? Beside the nice cell phone making its noise. It's okay, I got the sledgehammer under here, I'm ready. I'll tune up that cell phone. The next sound it will make is and it won't make any more sounds. What's the difference, this one versus 1822?
The volume is different.
Volume of what?
HCl.
Yeah. The hydrochloric acid solution volume is greater. In what way is it greater? Is it greater for 1841 or smaller for 1841?
Greater by 100 milliliters.
In 1822, we used 200 milliliters, or considered 200 milliliters of what was it? 10th molar? No. That's what we had for 1822. But for 1841, (300 milliliters). Okay? Well then, the quantitative inventory for this system is different. Now, I've already taken the liberty of writing, before we consider any reactions to occur, the QPSI. Here it is. .015 moles hydronium ion as well as .015 moles of chloride ion. Who cares? Because that affects the pH not in the least. Sodium ion, I don't even care about its quantity because that has no effect on pH. If it did, we'd have to tell you. Sodium ion does not form a well-defined hydrate. Its positive charge density is insufficient. Doesn't affect pH like aluminum ion in water solution or some such metal ion with a high positive charge density. Hydroxide ion, hydrogen sulfide ion. Okay? Chemistry. From our inventory, we know the strongest acid of consequence in the mixture we make is hydronium ion, strongest base, hydroxide ion. Extent of this reaction is essentially 100%. Its K is 10 to the 14th. I think we can take that as 100%. By this reaction, how much hydroxide ion did we murder? 0.010 moles. And so, by this reaction, how much hydronium ion did we murder? 0.010 moles. Okay? So after this reaction, we still have how much hydronium ion? 0.0050 moles hydronium ion. That went away. Is there anything else in this system with which hydronium ion can react effectively? What is that something else? HS minus. HS minus. The products of this reaction respectively will be H2S and water. What will be the extent of this reaction? Practically speaking, 100%. I'll write down V large. Or V dot LG dot for very large, okay? Tell me, in doing this, how much of the hydronium ion gets clobbered? All of it. How much of the hydrogen sulfide ion gets clobbered?
0.005.
Kill 0.0050 moles. Make 0.0050 moles. And so at this point, what need I do again? Reconsider my inventory, you betcha. Because it's the system species which dictate any chemistry exhibited by the system. Well, how much hydrogen sulfide ion is left? So we'll write 0.0050 moles HS minus remains. And at this point, I want the hydronium ion concentration. Or if you prefer, pH. What do we do now to proceed? At this point, do we have a buffer? Do we at this point have a buffer?
Yes.
What are the components of this buffer?
Hydrochloric acid.
What?
HS minus H2S.
What are the components of this buffer?
HS minus and H2S.
That's right. Hydrosulfuric acid, that's the name for H2S, about which I could care less. Let's call it H2S, that's fine. And HS minus. Chemistry class, reading formulas, provided the formulas you read are correct, that's always the best way to get at it. The hell with names. If you call me X throughout, I don't give a damn. If I succeed in getting you to understand some chemistry, that's what matters, not what my name is. That doesn't matter. What reaction would you like to write to get at pH? How about this? You see how this reaction equation just gets us exactly where we need to be? Because this reaction equation contains both principal system species and hydronium ion. And that's what we want to compute, right? Hydronium ion molarity? So tell me. I'll give you a hint. Look at the acid-base table. Look at your acid-base table. And as you look at the acid-base table, I want you to tell me the hydronium ion concentration for this system. What is it?
1.1 times 10 to the negative 7.
I like that. How many are baffled by this? Or do you all see where this comes from? Are you looking at the acid-base table? Are you looking specifically at H2S? You see Ka for H2S. Because if I write the Ka expression for H2S, I'm going to see hydronium ion molarity times HS minus molarity divided by H2S molarity, right? That's what I'm going to see. And for this system, how do the HS minus and H2S molarities compare? There you go. All done. How about that? All right, we go to 42. (42) is really not a buffer problem, but it does bear an analytical similarity to a buffer solution, because as we will see in 1842, the recipe x squared over m sub I minus x does not apply, because this will not be a single solute system, at least not for the second part of 1842. Let's start with the first part of 1842, which involves 5.0 milliliters of deionized water treated with 5D for drop of 0.50 molar HCl. How many of you remember back to Chemistry 2045 laboratory assignment number 1, where we asked you to do a very difficult, challenging activity, count drops in a milliliter for aqueous fluid? How many remember that? You remember roughly how many drops in a milliliter of aqueous fluid? 20. You betcha. Hey, that's handy information. It's daggone handy for 46 laboratory, because you're going to have to use often in 46 laboratory small quantities of solutions, which will be obtained by diluting parent solutions. Like if you need 10th molar, 100th molar solution of something in 46 lab. Hey, we can't keep putting out just 10th molar and 100th molar solutions. We got too many of you. Now for C-term, we could do it. We don't have that many folks for C-term. But my golly, in spring, for example, there are over 1,000 people in 46 laboratory. Hey, you think I want the stock folks wearing out their shoes on a daily basis, running back and forth? More solution is, make some more, make some more, because they're using it up. Hell with that. I put 6 molar there. You can make your own by dilution, which means you better know how to make dilutions. And you better make the right quantities. If we tell you to make a milliliter, make a milliliter. Don't make 10 milliliters and throw away 9 milliliters. If you do that, I'm changing your lab grade to E, and at UF, that does not mean excellent. Okay? But if I have a 1 molar parent solution, for example, and I need 1 milliliter of 10th molar, hey, what do? I need to make a 10-fold dilution, don't I not, to go from 1 molar to 10th molar? So I got this 1 molar solution looking at me. I need 1 milliliter of 10th molar. What do? I take 2 drops of my parent solution and I stir it up thoroughly with 18 drops of water, and there I go. I don't need to fool around with graduated cylinders and cleaning and rinsing and all that kind of stuff and trying to pour the whole milliliter volume out of the graduated cylinder, which for aqueous liquids is not easy to do because I'm bound to leave some of the solution behind because because glass is hydrophilic. What's that mean? Water liking. Hey, they're electrically alike. Water has a tendency to stick rather strongly to glass. Now then, here's this system. 5 drops. Well, if there's 20 drops in a milliliter, 1 drop has a volume of how much? 0.05 milliliters. So 5 drops volume is how much? Milliliters. Bingo. Okay? So to figure out the hydronium ion concentration for this system, I figure out how many moles of hydronium ion I have in 5 drops of my half molar HCl solution. And I divide it by my solution volume, which in milliliters is 5.25 milliliters. Nothing fancy about this. This is simple solution stoichiometry. This will give me a hydronium ion concentration of 0.024 or 24. 0.24. 0.024. Okay? You can do the arithmetic. You know what to do. Now, this is part A. Part B is the fun part. Now, as this question is stated in the notes, we have to make a change. I'll tell you why. The first thing you want to do is to look at question 1842 as it is stated in the notes, where it says 5.0 milliliters of half molar acetic acid. A volume which is the same as our deionized water volume up here, okay? And we're going to change that acetic acid solution to 0.53 molar. Okay? And we're going to add to that 5 drops of 0.50 molar HCl. Anybody like to venture a guess why I asked you to change the molarity of the acetic acid from 0.50 to 0.53? Does this mixture dilute the acetic acid? Does making this mixture dilute the acetic acid? Does it? You're daggone right it does. And I overlooked that when I first wrote this question. Okay? So I'm going to write here. By dilution, this gives, the acetic acid solution that I wanted to deal with. You can do the arithmetic, it's not hard. So, in sum, we now have 5.25 milliliters of 0.50 molar acetic acid, okay, which contains the same mole quantity of hydronium ion, at least initially, as this system, right? Because in each system, I've added 5 drops of 0.50 moles of hydrochloric acid solution. Okay so far? Now we get to the $64 question. Will the hydronium ion concentration for this solution Q for this solution, will the hydronium ion concentration be the same as the deionized water treated with the 5 drops of DHCl? That's the question. Put another way, if we had acetic acid solution alone, or for this acetic acid solution, this equilibrium is alive and well in that system. The question is, if I had 0.50 molar acetic acid solution all by itself, we would use this equilibrium reaction to calculate the hydronium ion concentration for the solution if we wanted it. We talked yesterday about 0.50 molar acetic acid solution because we prepared some by demonstration, didn't we? We had 1 molar acetic acid, mixed it up with an equal volume of deionized water, and I asked you, predict the color. And some people were thinking about orange with red and all that stuff instead of thinking about chemistry. But if you think about chemistry, then the answer is obvious. Because this is chemistry class. I think you know that by now. And it will be nothing but chemistry class, so long as this body is standing in these shoes. Isn't that what's supposed to go on in chemistry class? Question. When I add an external source of hydronium ion, because that's really what's going on here. I got this equilibrium in my acetic acid solution, but in this case I'm adding an external source of hydronium ion. That's my 5 drops of 0.50 molar HCl. What impact does that have on this equilibrium reaction? Which of these reactions does the added source of hydronium ion provoke? This way or this way? This way or this way? Which way? Does it make this reaction go further as written, adding this? Or does it make it go this way? Which way does it go?
Right to left.
Right to left. In other words, by treating this acetic acid solution with the external source of hydronium ion, what am I doing to the ability of acetic acid to ionize by reaction with water? Am I increasing that ability or decreasing that ability? Decreasing that ability. And if I've decreased that ability enough, then it's entirely possible that the hydronium ion concentration for this solution is the same as the deionized water treated with the HCl solution. What do we do to find out? There's the thing. Well, hydronium ion concentration for this solution be 0.024 molar. If it's not 0.024 molar, then it will be what? Bigger or smaller than 0.024 molar? Bigger or smaller? Is not my solute an acid? An acid which is stronger than water? So if this isn't true, then the hydronium ion concentration will compare how to 0.024 molar? Bigger. Chemistry, always think about the chemistry of the system. Otherwise you're doing meaningless arithmetic. All right, here we go. Now then, let us make an algebra definition. Let us represent the molarity of acetate ion established by this equilibrium reaction. Because this system clearly contains acetate ion, and the only way it contains acetate ion is by establishment of this equilibrium. So I'm going to make an algebraic representation of the acetate ion molarity and call it wonderful X. Okay. Okay? So if that be true, since I have really 0.50 molar acetic acid, because we factored in the dilution effect, what will be the equilibrium molarity of acetic acid? It starts at 0.50. Minus X, right? Is that the derived species? Now, for this system, what is the equilibrium molarity of hydronium ion? Don't tell me X. Don't tell me 0.024. Plus X. Ha ha. Are we seeing this? This came from the added HCl solution. And the establishment of this equilibrium tells me that if this equilibrium makes X moles per liter of acetate ion, then it must also make X moles per liter of hydronium ion. But I got two sources of hydronium ion. The HCl solution I added, plus this equilibrium reaction. So, how do I get the hydronium ion molarity for the solution? I add these up. There we have it. Okay? Now for a significant figure question. If this equilibrium, as it is established in this solution, the acetic acid solution which has been laced with an external source of hydronium ion, if this equilibrium proceeds to such a small extent left to right because of this hydronium ion that I added, then how will the equilibrium molarity of acetic acid, compare to its initial molarity of 0.50? Did we follow the statement?
No.
If the added hydronium ion has stopped this reaction from making a measurable contribution to the hydronium ion concentration. I'm saying the same thing, I'm just saying it a slightly different way. Okay? Okay? If the added hydronium ion stops this equilibrium reaction from making a contribution to the hydronium ion molarity, in other words, has stopped the acetic acid from ionizing to any measurable extent, how will the equilibrium molarity of acetic acid compare to 0.50? That's the initial molarity.
It'll be higher.
Pretty much the same.
Lower or
Same! Right? You remember initially, what have I got here as principal species beside chloride ion and water? What have I got here?
acetic acid.
I got acetic acid and hydronium ion. That's it, right? I don't have an external source of acetate ion here. I can't get any acetate ion in this system unless this thing goes. Now then, 4. .24 plus X to equal 0.24. In other words, we're operating on the basis that perhaps this equilibrium reaction, which is going to be established in this system, no question about it, but it will not make a measurable contribution to the hydronium ion concentration. Is that possible? Is the hydronium ion concentration for this solution 0.024? Well, if that is possible, then 0.024 plus X equals 0.024. Then X must be less than what value? Significant figures. For example, if X equals 0.001, does 0.024 remain the same? No, then it becomes 0.025, doesn't it? All right. What if X equals 0.00060? Will this value for X on being added to 0.024 cause 0.024 to become 0.025? Yeah. All right. But what if X is this? Now I got a judgment call, don't I? What's the judgment call? When I got 5 at the end of a number that's to be rounded, do I go up or down or stay the same? Up, down, or stay the same? I like to play stay the same. That way, if I keep staying the same, then for all the times it should have went up will be counterbalanced by all the times it should have went down statistically. So I'm going to write this. Because now we won't have any arguments, will we? If X is this number or a number smaller than this number, then 0.024 does not change when I add this number to 0.024. We agree with this? So, what I'm going to do is to put in 0.0005. Because I've already said, if it's 0.0005, then 0.024 can change. Well, let's put in 0.0005. All right? And imagine this becomes 0.025. This is 0.005. What have I got down here? Okay? That's the arithmetic I got to do. Now, when I do this arithmetic, equals a number which is greater than 1.8 times 10 to the minus 5. What's that mean? If I do this arithmetic and get a number that's bigger than 1.8 times 10 to the minus 5, in fact, what I'll get is about 2.5 times 10 to the minus 5. What's this mean? What's it mean about the value for x? The correct value for x. It's got to be smaller than 0.0005. So guess what? The hydronium ion concentration for, oops, I erased part of it. The acetic acid solution treated with hydronium ion is exactly the same as the DI water treated by hydronium ion, because the added source of hydronium ion looked over at acetic acid and said, "You can't go any place now." This is really just showing you Le Chatelier's principle in operation. We whacked this equilibrium by adding an external source of hydronium ion. We whacked it to the extent that in this solution, the one we prepared, the ionization of acetic acid does not contribute at all to the hydronium ion concentration for the solution. Now you know that wouldn't be true if I hadn't put the hydronium ion in there. Ha-ha! But I put the hydronium ion in there and that changed the game considerably. So I repeat, the parallel that this problem draws to the buffer systems is that for this system, the hydronium ion molarity and the acetate ion molarity are nowhere near the same. So does x squared over m sub I minus x apply to this system? Hell no. We'll pick it up from this point tomorrow, and the stuff we get through tomorrow will complete the material for which you will be responsible on exam 1. Or else someplace in between. I'll decide as we go through the material.